We're starting some new videos for Math 100, Chapter 1.1. And what this section is about is basics of algebra. And this is the booklet we're using. Now each of the students will have a reduced copy of this. And the nice thing about it is that along with the examples, we give you the answer key. So the answers are there. Now what's not included is how to do it. And that's what this video will be helping with. The first four examples are fill-ins. They give you the words up on the top, and then you want to see if you can write these in. And again, from the lesson that we have in class, you should have some of this knowledge. And then, of course, you're going to study what you learn so that you can remember it. So we'll jump into example 5, where the general process of what we're doing is substitution, where we take a letter that we find in algebra and replace it with a number value. So there is a technique for this, and that's what I want to show you. So the 3 we know is there. Now when there's no sign between a number and a letter, it indicates that you're going to multiply. So to indicate that, we could put that in parentheses, that whatever the n is, in this case it's going to be 5. And then in the case we put our negative there, our 2 there, and now we're going to replace the m with the 4. And then now it's just a matter of calculating using arithmetic. So this is 15 minus 8 will give us a 7. All right, in this case, again, we're going to just take the letter that's there. In this case, it's A. So we'll put the A in parentheses and put the number 10 there. A is 10, and we're going to square it. And then we're going to add 9. And then there's our negative sign, and we're going to put B in there. And since it's not multiplication, we can just put the 5. So we're going to square 10. That will give us 100. And then we're going to subtract the 5 from the 9, and that'll give us a 4. So we get 104. So what we're doing here basically is just some substitution. Now in number 7, notice it gets difficult already, but hopefully you've developed a pattern of how to do it. You're going to put the 5, parentheses for the x, and we say the x is 2. And we're going to square that 2. Then we're going to put a y in there in parentheses as a 3. So we've just changed it from algebra to arithmetic by replacing the letter, the variable, with a known value. X is 2. Now the y, which is 3, is the one that's squared. And over the years I've found, as long as you follow a pattern like this, and the use of a parentheses here is a very good device. So we're just converting it now. 5. 2 squared is going to be 4. We can also use a dot to indicate multiplication. And then times 3. Plus 3 times 2 times 3 squared is 9. And I'm assuming many of you are going to use your calculators to actually calculate this. we were missing the bottom of this, so I moved it down a little bit. So picking up, 5 times 4 is 20, times 3 is 60. And then 6 times 9 is 54. And when you add them together, that's 114. Now, as we continue on order of operations, this one is particularly interesting because all of this is within a bracket, and then it says divided by this. So it creates a little bit of a problem because when I did it, following this explicitly, I get a different answer than what was in the textbook. So let's do it another way. So basically we want to get our 11, replace the R with the 3, the 4 for the S, and then divide this by 2R. And I believe this is the way it has to be done because of the parentheses. So let's work it through. This becomes then an 11. This is going to be a 7. So minus 7. And then we're going to square that. And then divide it by 2. And we should replace the R with a 3. Okay, that's a little tricky. So this is going to be a 4. That we're going to square. And then divide it by 2 times 3. So 4 squared is 16. 16 now was all of this in the bracket. That's divided by 2, because that comes first. We can't do that multiplication. We have to do the division first. So 16 is basically this. So 16 divided by 2 is 8. 8 times 3 is 24. And that's the answer. Because if you do this multiplication first, that's incorrect. You have to do the division first. Whatever comes first as you go from left to right. Okay, in this next part, they're giving us what is called an equation, where you have an expression, there's a series of terms, equals something. And we're still going through this process of replacing a letter with a number. And we want to see if we replace the T with the 1, it'll make this true. So again, we're just replacing. 16 minus 3 times T as 1. Does that equal 1? Well, we get 16, when we multiply this, we get a negative 3. So 16 minus 3, does that equal a negative 1? And the answer is no. So this is a no here. In the next one, we'll write it again. 16 minus 3 but we're going to have t as 5. So in a parenthesis, we put a 5 equals 1. So again, a negative 3 times 5 is going to be a negative 15. 16 minus 15 is 1. So yes, that is correct. And then I'll erase these to save a little room. Then we go to replacing this with a 15. So 16 minus 3, and we're going to put a 15 to replace the t. Does that equal 1? Well, this is going to be a negative 45. That's not going to be true. So this would be a no. And that's how you do those. This next one is an inequality, where we want to see if we replace the variable x by those numbers, is this still a true statement? So our technique is similar. 5 times 2 minus 8, is that greater or equal to 7? Well, this is going to be a 10. 10 minus 8 is going to be 2. Is that greater or equal to 7? No. So this would be no. And then now we're going to replace it with a 3. 5 times 3 minus 8, is that greater or equal to 7? So this is 15 minus 8, and this becomes a 7. Now is 7 greater than or equal to 7? And the answer is yes. And then the last one, save some room. 5 times 4 minus 8. So this is 20 minus 8, that's going to be 12. Is that greater than 7? And the answer is yes. Okay, again, we're showing you the technique. Carefully replace the variable with the given quantity, work it through, make your decision. Here we're going into some set builder notation where we're going to put our values using a bracket, or brace I should say, the set of all natural numbers that are multiples of 100. Well, the first natural number that is multiple of 100 is 100. And we separate the members or elements within a set by a comma. The next one will be 200. Next one, 300. And we've set up a pattern so we can use our ellipsis, and we just close it up. This is set builder notation. And then here's all the members of the word math that are in a set. So again, M, separate them by commas, set builder notation. Again, you'll be doing some of these in your practice. And then when you think you are ready, you move on to your quiz-bees. All right, in number 21, they want us to convert from the set to set builder notation. So here's our set of numbers, and we're saying that x is such that x is, now as we look at it, what are those numbers? And they're integers. And they're between something, aren't they? And what are they between? Well, it's not between -3, because -3 is in the set. So the integer that would come before is -4. And what would be the number after 3? 4. And that would be the set builder notation for this set. Now again, the elements of the set are what are listed there. These are sometimes called members of the set. Now, for something like this, when they're talking about even numbers, you wouldn't start to list them because that would be sort of impossible. But to put it in set builder notation, now remember, you could write it this way. In fact, let's do that. Even numbers between 1 and 11. So the first one is going to be 2, 4, 6, 8, 10. That would be another way of saying what they're saying here. And to put it in set builder notation, you would say x is such that x, and you just have to write this out, is an even number between 1 and 11. And by the way, sometimes when you're doing work and practice and in the quiz bees, and then even on the test, if you don't understand something, on the practice particularly, you can get the wrong answer and see what the correct answer is. And that will give you a form of how they want you to do the answer. Now on a test, again, if there's a little, whether they wanted this or they wanted this, you could ask me, and I will tell you. This is not a secret, if something is a little unclear. All right, for these next few examples, and we're doing a couple of them, 23 to 26, we're going to deal with is something, a natural number, a whole number, an integer. Probably should, not to confuse it with irrational here. Rational, irrational, and real. And in class, we gave you a little review of this, but let me give you another review here. Now, these are different sets of numbers. The natural numbers, as you recall, are 1, 2, 3. And we write that set as one, two, three, and then the ellipsis indicates that it continues on to positive infinity. This side is negative infinity. And we have graphed the natural numbers on this number line, and because of the arrow, this pattern continues. Now, if we add a 0 to the natural numbers, we get the whole numbers. So that would look like this. And then if we take numbers that are whole numbers on this side and their opposites, that is by adding this to this and ending up with 0, when we add that group of numbers, whole numbers and their opposites, we get the integers. And that would be indicated as ... coming from negative infinity to, let's say, negative 2, negative 1, 0, 1, 2. This would be the set builder notation for integers. And this is the graph of it. Now, are there other numbers on the number line? Yes. As we say right here, there is 1/2. There's also 1/3 there. Now, these numbers, if you convert them into their decimal form, 1/2 equals 0.5, and 1/3 equals 0.3, and the 3's repeat, such that it terminates as it does for 1/2, or repeats as it does for 1/3. These are also on the number line, but they're not any of these three. There are our next group of numbers called rational numbers. And rational numbers are most of the other numbers on the number line. Now we also have one other number, like, well, there's a couple of them, of course, right about here, which is the square root of 2. Now, the square root of 2, if we convert that to a decimal, it doesn't terminate. On your calculator it does, because it always estimates it. But in real life, if you kept checking it out, it would keep going on and never end. We say it doesn't terminate, nor does it have a repeating pattern. If it doesn't terminate or have a repeating pattern, and it's like this with no termination, no repeating pattern, we say the number is irrational. But notice it is on the number line, as is pi over here too. Pi is irrational. So some of these numbers are various categories, but all of the numbers are what we call real numbers. They are on the number line, and that's the numbers we'll be dealing with in this course. So there's a little brief review, and now we want to identify. Well, what is this? Is it natural? No. Is it a whole number? No. Is it an integer? No, because of the decimal part. So this number is a rational number. It's on the number line, but not one of these others. And all of these numbers are real numbers. That's the same for this one. But this one happens to be all of them except irrational. This is a counting number or a natural number, a whole number, an integer. It's also rational, and it's a real. Now 4 is not these two, because negative numbers are not whole numbers or natural numbers, but it's an integer, and it's rational and real. And 0 is a whole number, it is an integer, it is rational, and it is real. And this one is rational and real. And here's the only one that's irrational, but it's also real. So a little summary, and hopefully helpful, and something for you to study, and you'll have to, because you want to be able to master these skills and end up with right answers. One other little comment though, before we go on. Sometimes you see the square root of 4. Now that's under the radical sign, But the radical sign is just an operation. It says take the square root. Well, the square root of 2 is this fraction here, decimal fraction, that doesn't terminate, just goes on. So that's why that's irrational. But when you take the square root of 4, you get 2. Any number under the radical sign that's a perfect square would be rational. Okay? And in this case, it's also a natural number, a whole number. So you'll be challenged to work with some of these as you go on. Okay, one other, or two others to wind this up, is these last two, where they give you some definitions. They're saying that Q would be the rational numbers, Z would be the integers. I wrote that there, and that's in your booklet. Now these symbols are new. This symbol, and you may have had it years ago, it's kind of a C with a line underneath it. This is a subset. Subset symbol. And this sort of a funny kind of E there, this is a element of. So this is sort of like a member of a set. So let's read this. Natural numbers are a subset, that is, it's sort of below that in that chart, of rational numbers. And this is true. Natural numbers are a subset of rational numbers. Now, 12.8, is that a member of the set of integers? Well, this is a decimal fraction. Integers don't have any fractions in it. So this one is false. Again, what they're asking you is to be familiar with the various kinds of numbers. And again, lots of stuff to read over. Depending where you are, you'll have to do some things. Take some good notes, study, give it your best shot.